So welcome everyone to this morning session. Let's get started. We have David Weld from UCSB giving some more pedagogical lecture on cold atoms and quantum simulation. So it's great to have an experimentalist explain us how all this stuff really works. And so, yeah, the floor is yours, David.
Okay, thank you. Thank you so much for the introduction. Thank you for having me virtually. And I really wish I was there in person. I was planning to come in person and it didn't work out, which is very sad for me because it would have been my first trip to India. So sorry to miss it, but I really hope that we can get a good discussion going today for this sort of first of two talks. And this is a more pedagogically themed talk. So the title I put here is Cold Atoms, Quantum Simulation and Driven Quasicrystals. And this is a approximate outline of the talk, and this really covers both today's talk and tomorrow's talk. And maybe it divides neatly between these two subsections. I guess we'll see. So what I wanted to do starting out is give an introduction, really zooming way out to from an experimentalist point of view to the field of cold atom quantum simulation. So I want to talk about where I see cold atoms fitting in the large space of quantum platforms, all possible quantum platforms, actually, and then describe a few features of cold atom experiments that I think are important, and then a little bit about topics of current interest. And that sort of makes a lead in to the a discussion of recent research results, which are relevant to the topic of this program, a couple of the topics of this program, actually. And what I want to talk about there is different studies of localization in driven quasicrystals. And at the end, maybe a little bit about some of these new directions like quantum interactive matter, which I'm very excited about. So yeah, the outline divides up into a pedagogical introduction, which I hope is like unusual enough to provoke questions or outrage in the audience, and then something that sounds more like an ordinary research talk, which maybe will be mostly tomorrow. So to begin with, what I want to do is say where I see cold atoms fitting in the broader space of all quantum experiments, or even all experiments. So if we want to do quantum simulation or quantum experiments, we want to use something quantum mechanical. And the good news is that doesn't limit us. We can use anything. It appears that quantum mechanics describes the whole universe. Not only, obviously important technologies like transistors, but also important technologies like knives depend on quantum mechanics completely for their properties and any kind of reasonable understanding of their behavior. So given that undisputed truth, you might think that the features of quantum mechanics that people find fascinating, like entanglement, superposition, the wave-like nature of particles, and so on, should sort of be ubiquitous and visible in everyday phenomena. But of course they're not, at least not directly. And if you want to make a technology or an experiment which uses these delicate quantum phenomena, you need two things really. And those two things are isolation and control. So any kind of quantum experiment has to do something like these things I'm about to sketch in these coming slides. So you take the whole universe, which is quantum mechanical, you cut out some subset of it, which is in your lab, and you protect it from everything else in some way. If it's allowed to entangle fully with everything else in the universe, then you're not doing a quantum mechanics experiment, you're doing a classical mechanics experiment. So you need this sort of fence that protects it from the rest of the universe, but not perfectly. You need a little channel between your experiment and the rest of the universe, because the rest of the universe is where you live, and you need some tool to control your quantum system, speaking in the most general terms. So I think that really any experiment that has quantum flavor, from cold atoms to superconductors to trapped ions to defect centers, liquid helium, whatever you want, has to have basically these three features. And the need for isolation and control that arises from that general cartoon of an experiment in quantum science gives rise to certain desiderata for quantum platforms. So these are things that we want to have if we want to make a platform that we can make good qubits out of or do good quantum simulation experiments with, or do quantum sensing with, or quantum communication, or any of the other technological or scientific endeavors that we would want to pursue with a quantum mechanical platform. So these desiderata, which are basically an adaptation of DiVincenzo's criteria for a good qubit platform, I've listed here. So you need something that has robust quantum mechanical states that you can reliably prepare in some particular state. You want to be able to move it among different quantum states. So that's reliable universal family of transformations. And you need to be able to measure the resulting state of the system in some way. Those are all just restating the famous DiVincenzo criteria for quantum computing platforms. And then the fifth one here is extremely important from an experimentalist point of view. And that's that whatever quantum platform you choose, and here I'm going to be situating cold atoms, but I want to kind of talk about all the possible quantum platforms. Whichever one you choose should effectively leverage things that Homo sapiens is already good at. So if you're building something on top of silicon fab, then that's good because people have already spent $100 trillion getting good at silicon fab. We're much better at that than we are at various other subfields of technology. So whether something is using a capability we're already good at is actually just as important as these other criteria. Okay, so what I want to do now is just zooming way out, think about what physical objects can fulfill these criteria for doing a quantum experiment. And again, I'm trying to really be provocatively broadly zoomed out here. So I hope to provoke questions or an interesting discussion. I really urge people to interrupt any time to discuss. All right, so what can we use to do quantum experiments of the kind that I have extremely vaguely and broadly sketched out in the beginning part of this talk? Well, this is the complete menu, I believe. If we want to build something, it should be taken from this menu because this is everything we know about. So these are the standard model particles, the quarks, the leptons, the gauge bosons, and of course the Higgs. And then there's a few things that we think don't fit in so well to that list, but we kind of know they're probably out there. So I added them over here on the right. Do you guys think I'm missing anything from this list? I can't tell if you're even able to answer questions at the moment. But I guess, I don't know. I may
like everyone is enticed by your question, but no one knows what.
Okay. I don't know of anything that's missing here, but a lot of the things on the list are ridiculous. And we're not going to do make quantum mechanical experiments out of them. So I think very quickly, like somebody with a lot of food allergies, you can take this complete menu and knock it down to a complete or reasonable menu that we could potentially order off of. So I don't expect too much dispute from crossing off all the things I've X'd off here. I don't know what the most realistic quantum platform that I've X'd off is. Maybe, I don't know, a muon, I guess, is probably the most realistic, but even that is not all that realistic. They don't live very long. So we're left with a very restricted subset of what I think is really all possibilities for building a quantum science experiment. And this is what that restricted palatable menu is, which is photons, electrons, and up and down quarks. And of course, recipes made by combining various ones of these. So what I want to do now is just sort of step through the possibilities here, different combinations of these four types of particles, and talk about how you could use them to build a quantum science experiment. And people do. People use all different kinds of combinations of this to build quantum science experiments, and they have various strengths and weaknesses. And a good opportunity, I think, for us to discuss would be to talk about these different platforms that aren't cold atoms, because I don't say that much about any of them, but I would be certainly interested to discuss. So I think the first place to start is with that nice red gauge boson, the photon. And this is in some sense really the ideal ingredient if you want to build a quantum mechanical experimental platform. Photons have spin. They're easy to control. We have a lot of technologies for controlling photons. We can even detect them with our bodies. At some frequencies, we're really good at creating them and detecting them. At some frequencies, we're less good, but there's a wide range of possible frequencies. We can make them, we can move them around, we can see if they're there, and to some extent, we can isolate them from the rest of the universe. You can put them in cavities, or in quantum gases even, and sort of temporarily keep them apart from the rest of the universe. So these, photons make a really intriguing and beautiful quantum platform that's pursued in a variety of labs. The trick with photons, the weakness, or the thing that ends up being hard if you use photons to build your quantum science experiment, is getting them to interact with each other. So nonlinearity for 2-qubit gates is pretty hard because the equations of electromagnetism are linear to an excellent approximation. And so making something like a single photon optical transistor, which you might want as a building block of a photon-based quantum platform, is technically at the edge of possible. For low frequency photons like microwaves, you can use matter to introduce anharmonicity. So you can use, for example, a Josephson junction made of superconductors. And what that does is it takes a trapped photon and it makes it anharmonic, makes it so that two photons have a very different energy than 2 times 1 photon. And I'll talk more about that when I come to quantum platforms based on actual matter. But for photons, I think this is really one of the drawbacks is they're very linear, but very wonderful quantum objects for sure. And I won't attempt to enumerate all the different photon-based quantum information processing platforms or the other ones that I'll talk about, except for cold atoms. But I certainly would be happy to discuss or to hear objections to any of my generalizations here. The next thing from our menu of everything is the electron. So electrons are also pretty great when it comes to doing a quantum science experiment. They are sort of our picture of a spin-a-half system. A lot of quantum mechanics textbooks just start with a discussion of the physics of spin-a-half systems, and that's what an electron is. It's not pretending to be that. That's exactly what it is. It's stable. They're all over the place. I've got several electrons right here in the room with me, and you guys probably do too. And they have a monopole moment, unlike the photon. They have a charge. And this is actually pretty handy, but it's also a double-edged sword. You need, in general, if you want to do a quantum science experiment with electrons, to keep them around and not just have them run down a wire or through a vacuum far away from you. You need to keep them in some region of space. And this gives rise to the need for trapping. And the need for trapping is actually common to almost every quantum platform that I'll be talking about. I talked about it also in the case of photons, because that's what a cavity is a trap for photons. So for trapping electrons, you have a few options. You can trap them in semiconductor nanostructures, which is great because it leverages our capabilities to fabricate silicon and gallium arsenide and things like this. You can trap them in more exotic environments, like the surface of a droplet of superfluid helium or solid noble gas. And there's a variety of fascinating and beautiful, pretty recent experiments along these lines that I think are very exciting. Or you could always trap them, the same way you would trap an ion in a Paul trap. And I'll just tell you my personal opinion is that trapped individual electrons are an underexplored platform for making quantum computers and for quantum science. I think there's some pretty cool possibilities there. There's just a few people looking at this, and I think it could be a very exciting area. That's my amateur opinion. That's not what I do. Okay, moving on up our mass hierarchy on our standard model menu. We have the up and down quarks, and they're not going to work by themselves because it's naughty according to the characteristics of the strong force. So they have to be put together into nuclei or nucleons. And using nucleons, or let's just say nuclei, assemblies of neutrons and protons, for quantum science is well explored, and it's actually one of the earliest quantum information processing platforms that was really viewed as like making a real quantum computer in liquid state NMR experiments. So these are there's a lot of good things about nuclei. They're very nice and isolated from things like electronic degrees of freedom. And so they can have long coherence times and be beautifully quantum mechanical. State preparation can be a surprisingly tricky issue. Taking a nucleus or an assemblage of nuclei and putting them in the state you want, unless you're interacting them with electrons to do it, is actually pretty challenging. But this is something that's been reasonably well explored. I wouldn't say that it's currently at the forefront of like quantum computing experiments, but it is a beautiful quantum science platform that's a lot is known about. Much less is known about the possibility of using not nuclear spins, but nuclear energy levels to do quantum experiments. And this is totally science fiction, of course. This is utterly impossible with current technology. But it's not so obvious to me that one shouldn't be able to do some of the same things that we do routinely with electronic degrees of freedom with nuclear degrees of freedom at some point. You need things like gamma ray lasers that we're not anywhere close to having to match our ability to control the electronic structure of atoms, for example. But if we had that kind of capability, I think in the decades or centuries in the future, nuclear energy levels may be an interesting playground in the same way that electronic energy levels have been for the last 100 years or so of atomic physics. And there's intriguing possibilities that some of you may be aware of, where you have nuclear energy transitions, which are very, very, very low energy for accidental reasons. And there's one of these famously in thorium-229, which is almost in the UV range of the electromagnetic spectrum. So could that be an interesting clock or an interesting piece of a quantum science experiment? I don't know, but it's a pretty cool possibility. All right, now we're getting to actually what I really want to talk about today, which is atoms, which is, of course, atoms are what result when you take the last two ingredients and put them together. You have electrons, which are negatively charged, and you have protons and neutrons, which bind together to form positively charged clumps. And you then put them near each other and they attract each other with a Coulomb force and create something which is more complex than any of the ingredients we've talked about so far. So atoms have internal structure. They have the electronic degrees of freedom I was just talking about. And that more complicated structure gives you opportunities for more complicated tools of quantum control. So things like optical pumping, where we use polarized photons to put an atom into a particular quantum sublevel, or things like laser cooling, where we use spontaneous emission and the interaction of electronic degrees of freedom with photons in order to actually remove entropy from samples of atoms. All those things, which are critical tools for controlling atoms in the kind of experiments that I do, are really possible only because atoms have that more, a step more complex internal structure than a nucleus or an electron or a photon. Like electrons, atoms generally need to be trapped in order to be useful for anything. So you need some way to hang on to them and keep them in one place so you can do experiments on them. And you can consider a lot of things traps, which maybe aren't typically thought of as traps. So I've arranged some possible traps for atoms from strongest to weakest in this bulleted list here. And at the top, the strongest way we know of to trap atoms is to actually make chemical bonds to them. And so in a sense, this is what, for example, an experiment that uses nitrogen vacancy center defects is doing, is it has an atom, or really a molecular ion, which is made of a vacancy and a nitrogen atom, and it's trapped by being part of a lattice of diamond. So it's not going anywhere because it's chemically bonded to the adjacent carbon atoms. And you could also conceive of dopants in silicon, donor or acceptor dopants in silicon, as being atoms. I mean, they are atoms, and they're trapped in the matrix of that solid by chemical bonds. That's an extremely strong trap, very hard to break out of. And that again, as I alluded to earlier, is sort of a double-edged sword. Strong traps are nice because it's robust. You can take a piece of diamond and put it near a cell and use an NV in the diamond for quantum sensing. That's awesome. On the other hand, the very strength of that trap also means that your quantum system is better coupled to the environment than it would be if you used a weaker handle to hold on to it. Okay, so moving up the hierarchy of traps to weaker traps, you can imagine using forces that absorb atoms to surfaces, which are weaker generally than the kind of chemical bond that exists inside a crystal. This is an underexplored area also, in my view. I have a little project looking at this, and I think surface science is kind of a jungle. You can easily get lost in it, but I think there's potentially some interesting possibilities for quantum science experiments that involve atoms that are adsorbed onto surfaces. Moving to even weaker traps, but therefore, in a sense, more quantum coherent, you can trap an atom using its monopole moment. So you need to endow it with a monopole moment by ripping off one of the electrons, usually. That gives it a charge, and you can then trap that atom using electric fields in, for example, a Paul trap, like we talked about with electrons. So this, of course, is a weird way to describe it, but a very familiar quantum science experimental platform, which is like what companies like Quantinuum do, or scientists like Chris Monroe do, which is trap ions and manipulate their internal state to do quantum science. And then moving to sort of the weakest possible kind of trap for an atom, you can use a neutral atom, which has no charge and therefore no monopole moment, and then needs to be trapped by its dipole moment. And this is my field. So this is the field of trapped neutral atoms, is the field of taking atoms and controlling them using their electric or magnetic dipole moments, potentially induced, which is, of course, a much weaker form of trapping than any of the other ones on the list. And therefore, these experiments tend to be at lower energy, but also much better isolation from the rest of the universe. So I'll come back to atoms and talk a little bit about those experiments in a second. But I just want to say, you can keep going up this hierarchy of complexity. So the next sort of item on the menu, by combining together the things we've talked about already, is probably molecules. And that just means put together multiple atoms, again, using Coulombic type interactions. And these are, fantastically more complex than individual atoms, but still, in a sense, perfect and identical in a way that solids aren't. So I've, because it's very late here and somewhat early there, I picked this particular molecule to put on the slide here. This is caffeine, and every caffeine molecule is identical and behaves like a perfect quantum machine, as long as you get all the isotopes right and there's not any enantiomers or something. But they're much more complicated than atoms, which gives you these potentially very large Hilbert spaces to explore and use even in individual molecules. So this is a huge frontier for the field of atomic physics. As an experimentalist, molecules always feel like the future for our field, but our experimental abilities are weak compared to what we can do with atoms. So something my colleague Dave Patterson likes to say is that nobody has ever put a molecule with more than 2 atoms into a single quantum state. So taking a molecule like this pictured here and doing the kinds of things that we do routinely with trapped atoms or trapped ions is still, a little beyond the capabilities of current science, but very exciting, and a lot of very smart people are working on this direction. Then, of course, if you put a bunch more of these together, at some point you get an actual crystal or an actual piece of material, and that's even, many levels more complex than a molecule. And at some point, if you have around a couple hundred of these things, you abandon the idea that it's a perfect and identical object, and you start to make statistical statements about its properties. And of course, solids and condensed matter physics is the study of these things is the majority of physics. And materials offer collective degrees of freedom, which can give you new capabilities that are relevant for quantum science. And some of those have quantum information processing applications, for example. So famously, superconductivity is an emergent phenomenon that exists when you have a material that's composed of a lot of atoms like this, and that's critical to the kind of Josephson junction qubits that I already mentioned once before in the context of photon nonlinearity. There are other degrees of freedom, mechanical excitations, magnetic excitations for electricity, and so on, which emerge in solids and are relevant for doing quantum science. And I mean, obviously can't even scratch the surface of elucidating a table of contents of this gigantic field. The one thing to add in here, which is important in the context of modern quantum science experiments, is that you can sort of generate new menu items using solid state physics of this kind. So you can get emergent excitations, which have properties, which are particle-like things that have properties that are not found in the standard model that we wrote down several slides ago. So the most famous example of that is anionic excitations, which have fractional statistics between that of a boson and a fermion, and these are potentially of interest for making topological qubits. So, okay, I think I need to probably stop my increasingly complex hierarchy of possible quantum science platforms before I get to things that might actually be alive, and that kind of concludes the first section of the talk, where I wanted to just say where I see atoms fitting in to the space of possible quantum science platforms. So now, before I go into more detail and a little bit more of a pedestrian approach to talking about cold atom experiments specifically, let me pause and see if there are questions or comments about this extremely broad brushstrokes picture of possible quantum science platforms.
There's a question. Wait, I'll get the mic.
So I just had a quick question about these electrons as quantum information platform that you mentioned. So what do you have in mind? One issue is that sort of cooling them, there are no lines, at least laser cooling or anything is out of question, right? Or yeah,
that's right, because they have no internal structure. And that's, like, in the sense that any quantum platform has to balance isolation and control, that's bad for control purposes, but it's kind of good for isolation purposes. So you have to cool them using electric fields, basically. It's possible to do like feedback cooling of a single trapped electron. This has been shown. And how far that can be pushed is, I think, a little bit of an open question, but it is a technology that exists. Just as a plug for another University of California researcher, I'll say that my colleague Hartmut Hefner at UC Berkeley has a project which is working on trapped electrons. And I think this graphic is even taken from him, although I'm not 100% sure of that, where they're trying to trap electrons in a Paul trap and see what they can do with it. But you're totally right. The things we take for granted in atom experiments, where we use the internal electronic structure to remove entropy or to image or to store information, those are out of the question. The only thing you're going to have is the spin flips, basically, to store quantum information. But that is the minimal ingredient. But yeah, I mean, great question. It's exotic. There's not a lot of people doing this for exactly the reason that you say.
There's no more questions right now, but
okay.
Yeah.
Nobody wants to know how to make gamma ray lasers to control nuclear energy levels? Those are backup slides. Okay, well, please do ask as we go along, or I don't know if people are thinking of other things to say now. I'd be delighted to sort of spitball about any of this stuff with you guys, either now or later in the talk. Okay, well, let me shift gears a little bit then, if not, and talk about the particular field that I know the most about here, which is trapped neutral atoms. And I'm going to talk about some particular features of neutral atom experiments. So, okay, this is a subset of a larger field of trapped gas phase atoms. And I do want to talk about three main currents of interest in this field, all of which are very active today. So you have trapped ions, which most people will be familiar with. It's probably along with Josephson qubits, one of the two, biggest and best established quantum science platforms. I hope you guys can still see me. I saw my video freeze for a second there. And it's a very well established quantum computing platform, for example. Maybe I won't say much more about that than I did already. Trapped ions use the charge to manipulate the ion, and that gives you a lot of control capability, but you also have to pay some environmental interaction costs. And then way down at the bottom of the list is my field, trapped neutral atoms. And I just want to highlight that a really exciting emerging area in this field. And I just went to DAMOP, which is the big conference for the American Physical Society's atomic physicists last week. And at DAMOP, by far the most vibrant and most numerous talks at the session were about this middle bullet point, which in some sense lies in between trapped ions and trapped neutral atoms. And this is, people call it tweezer experiments, which is a little bit misleading because optical tweezers have been used in a lot of other experiments. But what they mean is really optically trapped neutral atoms with Rydberg interactions. And that is a quantum platform that fits very nicely in between ions and neutrals, in the sense that instead of ripping an electron all the way off to make an ion, you rip it almost all the way off, 99% of the way off, to make a Rydberg atom. That's what a Rydberg atom is, for those of you who aren't atomic physicists. It's an atom which has had one of the electrons or more put to a very highly excited energy level. As you may recall from learning about the structure of hydrogen, you can put electrons in a higher and higher principal quantum number shell. There's an infinite number of those before you actually ionize the electron, but the energies tend to get closer and closer together as you increase the principal quantum number n. So that's what a Rydberg atom is. It's an atom which has an electron with a very high principal quantum number, on the order of 30 to 70, let's say. And this is an extremely promising, extremely active, extremely rapidly developing physical platform for doing quantum experiments. I won't say too much about it. This is like many people who are experimental atomic physicists, my group is actually building a platform along these lines. And at the end of tomorrow's talk, I might say a little bit about the goals of that platform if there's time. But what I want to mostly focus on today is a more traditional and a little bit better established technique of neutral atoms, which is to not use Rydberg interactions, but to use contact interactions and just work at very low energy density. So that's this third bullet point. But if people had questions or wanted to discuss Rydberg type experiments, I'd be very happy to also discuss this second bullet point, although I don't have slides about it. Okay, but fine. The thing I actually want to talk about is this third bullet point, which is neutral atoms that have interact via S-wave contact interactions. And these are often trapped in optical lattices, which is an interference-based trap that's very convenient for doing quantum simulation experiments of the kind that I'll be talking about. So of all the gas phase atoms, these are the most isolated because they're the most weakly interacting. They're also the coldest for the same reason. And they're the most numerous. You can get more neutral atoms together than you can charged atoms because they don't talk to each other. They don't repel each other very strongly. Those are all good things, but also, the flip side of those characteristics is you have the weakest control over neutral atoms of any of these three platforms, and the slowest as well. So typically, I would say that neutral atoms like this are not that well suited to gate-based quantum information processing of the type you think about with cold atoms, with trapped ions or superconductors. But Rydberg, tweezer-trapped Rydberg interacting atoms, I think, are going to be competitive or are already very competitive with the very best gate-based quantum information processing platforms. I would just put them in that same league already, really. Better suited for the neutral atom platforms that I'll be talking about are experiments in quantum simulation, and especially experiments in quantum dynamics. And maybe at the end of today's talk, or maybe at the beginning of tomorrow's talk, those are the types of experiments that I'll be actually discussing. So for these, let me pause here, since I sort of I'm not going to come back and talk more about ions or Rydbergs and see if there's any questions about these different types of gas phase atomic physics experiments, or how they fit in and what their capabilities are.
There's a question.
Do people study superfluids type physics with Rydberg atoms, or it's mostly done for lattice type simulations?
Good question. I don't know of such studies, although I don't think it's impossible, depending on the model of a superfluid that you wanted to set up. However, if you were really interested in superfluidity, I think contact interactions would be the way, because you can just make a superfluid. I mean, that's what this picture is here on the lower right, is actually a superfluid of lithium-7 from my lab, photographed in momentum space. So for studying superfluid turbulence or vortices or other interesting topics that have to do with superfluidity, by far the dominant approach, and I think a sensible one, would be to make a superfluid out of neutral atoms and then induce the interactions you wanted to see there. But I don't think it would be impossible to do it with Rydberg atoms. Just a little bit.
Possibly conceivably change some of the superfluid parameters using this Rydberg system.
Oh, very interesting.
Make it more quantum at even different set of parameters.
Yeah, so a very interesting possibility would be to have a little trapped BEC, a Bose-Einstein condensate, and then excite one Rydberg atom in that condensate and see, look at the interactions of that Rydberg atom with the rest of the condensate. That's very interesting. That's something that I'm personally interested in, because that's actually the unusual feature of the tweezer platform that we're building in my group, is it can trap little BECs at each site, not just individual atoms. So yeah, I think that's a very, very exciting direction.
Thank you.
There's another question.
So I can even
maybe announce your name so then they know.
Hello, my name is Duncan Odell. So my question is, for the gate-based operation, how these tweezers, how well do you actually control the positions of the Rydberg atoms in comparison to, say, an optical lattice, where I presume they're quite stable? In particular, you know, the dipole-dipole interaction is a very sensitive function of the distance between the atoms, and so if you don't control that well, I can imagine your interaction is rather sensitive to that, and so on. So is that an issue, or is that all that can all be overcome with these tweezers?
Great question, and you're totally right. It is an issue. It can. The answer is yes and yes. It is an issue, and it can be overcome. So the positioning of the tweezers is typically set by spatial light modulators or acousto-optic deflectors, and those are good technologies, but they're not as good as interferometers. So and making an optical lattice, that's an interferometer. It's really the wavelength of the light that sets the separation between the wells. That's an extremely stable type of trap with very well-defined, you know, tunneling matrix elements between sites, for example. It's very hard for tweezers to match that performance. And, you know, really good experimentalists in this field work hard at this and sometimes give up. So that is an issue in the sense that you don't have an interferometrically stable position in between the atoms. However, for gate-based processing, it turns out that that's basically fine. And the reason is that a typical way to generate entanglement between two tweezer sites would be not to create two Rydberg atoms and wait for a dipole-dipole interaction to wind up some particular quantity of phase, but rather to create one Rydberg atom at one of the sites, but you don't know which one. And that turns out to be very easy to do because of something called the Rydberg blockade. So if you have, imagine you start with your two empty sites and you create a Rydberg atom on one, my finger indicates a Rydberg excitation on this site. That can interact so strongly with the neighboring site that it can prevent the creation of another Rydberg excitation over there, or it can very far detune it so that you can't make it with the same laser frequencies. So what that means, if you just shine a Rydberg exciting laser on two traps that are sufficiently close, is you'll put them into a superposition of 0, 1 and 1, 0, basically. And that that blockade physics kind of doesn't depend so sensitively on the position as long as they're close enough together. So you end up not having to tune that so carefully and still be able to get usable entanglement. Does that make sense, Duncan?
Yes, thank you very much. Yeah, that's interesting. Yeah.
Yeah, very, very good question. And it's also, it would be cool to be able to control tunneling, for example, with tweezers. And people have done this, but it's really not easy compared to the case of an optical lattice. But it's an interesting possibility for sure.
There's one more question, I think.
Thank you. I'm Shayan. I wanted to know, where would you place dipolar quantum gases in optical lattices? Where would you place it in your hierarchy? Does it give us something equivalent to Rydberg's or better, worse?
Yeah, really good question. Maybe it should be on this list, honestly. I would put it between items 2 and 3. So for example, quantum gases of erbium or dysprosium, or I suppose molecules, has sort of stronger interacting and longer range interacting physics than trapped alkali atoms, but not as strong and not as strong anyway as Rydberg interactions. So I would put that intermediate here, and it's certainly a very exciting platform. I think if I give this talk again, I would add it as an intermediate bullet point. It's a good point. So people like my colleague Ben Lev at Stanford does beautiful experiments with dysprosium in Europe, people like Francesca Ferlino and others. And that not only does that add to the energy scale, but it also gives new, shapes of interactions. You can have anisotropic interactions, which give rise to very interesting physics. In terms of energy scale, it's very close to the kind of stuff that I do. I mean, those tend to be very cold, sort of nanokelvin scale experiments, not like the Rydberg experiments.
Since we are kind of adding more things to the list, but thinking about kind of making the photons quantum mechanically, saying cavities and combining those with these platforms.
I didn't quite catch the end of that, but are you saying experiments on photons?
Well, lattice-trapped atoms in cavities.
Oh, yeah. Oh, for sure. Yes, that's a key tool. And many people are doing beautiful experiments with that. Monica Schleyer-Smith and John Simon at Stanford, for example. I think all my examples are very California-centric, sorry. But yes, I think that's a beautiful toolkit, and that's an alternate way to introduce long-range interactions, for example, and non-trivial interactions among trapped atoms. You can study the physics of supersolids and things like this, for example. I would call that another axis to this list rather than another element in the list.
I think those were all the questions. Going once.
But it's not going to go away. There'll still be opportunities for questions on the next slide.
Exactly.
Okay. Yeah. No. Thanks for the great discussion. Zooming in on the particular lowest energy bullet point here, cold neutral atoms offer this particular balance between isolation and control, which is pretty far tilted in the direction of isolation. So when people who study quantum gases make a Bose-Einstein condensate, if nobody else is doing it at the same time, this is the coldest place in the universe. It's relatively straightforward to get these things down to the nanokelvin temperature range, and picokelvin is even achievable. And at these temperature scales and at these densities, macroscopic quantum phenomena are sort of right in your face. They're not hard to observe or to produce. And those include superfluidity, which was already discussed a bit, matter wave interference, and quantum phase transitions, for example. Neutral atoms do also give you pretty good abilities in quantum control, which is the flip side of the isolation coin. In some sense, I would say a Bose-Einstein condensate is the apotheosis of 50 years of development in quantum control in atomic physics, where what you've done is you've taken 1 million or 10 million or even 100 million at the outside atoms and put them in a single quantum state, so that not only do they have all the same internal quantum numbers, they're in the same external momentum state with coherence that's really unmatched by any other platform with that number of particles. And you have the ability, using various control knobs from atomic physics, to tune the Hamiltonian that those million or so atoms experience. You can change the kinetic energy, you can change the potential energy, you can put them in these lattices of different geometries, and you can tune how they interact with each other using tools like Feshbach resonances. So it's a field where there's a good, a very, very high degree of isolation, very, very low energy physics, but also a lot of interesting control knobs. And that's part of what makes the experiments that I want to talk about tomorrow possible, is all these different techniques of control that have been developed by atomic physicists for many decades. You can only do this kind of trick with some atoms. And that is basically because of the details of the internal level structure. So I think this is up to date, or has someone Bose condensed a new atom since I made this slide? It's possible that somebody has. So please feel free to ask a question if your favorite condensed atom is not on here. But this is at least, plus or minus 1 or 2 species, a complete list of all the atoms in the periodic table that have been brought to quantum degeneracy. So you have all the alkalis except for that nasty one down at the bottom. And those are easy to cool because they have a hydrogenic level structure that gives rise to easy cycling transitions and powerful laser cooling. Then when you get away from the alkalis, things get a little more challenging. If you use, for example, calcium or strontium, it's possible to, or helium, it's possible to kind of use those tractable 2-electron structures. And then there's other sort of moderately heroic possibilities: chromium, dysprosium, and erbium, which I already mentioned, and ytterbium, which ends up looking a lot like a group 2 element with 2 relevant electrons. And, much as one would like to make a BEC of carbon or nitrogen, this turns out to be just an extremely challenging endeavor. So for now, this is what's possible for atomic physicists in the area of degenerate quantum gases. The approach that we take to actually make these things is the fruit of, again, many decades of development in atomic physics, and a machine. This is a schematic of our ultra-cold lithium machine in Santa Barbara, and there are many others like it. I would call this an MIT-style machine. That's where I did my postdoc, and that's what this machine is sort of spiritually based on. And there's various technologies that we put together in order to bring these gases to quantum degeneracy. So we have atomic beams, we have laser cooling, we have trapping and control with various fields, laser fields, RF fields, and magnetic fields. And actually just those techniques, there's probably 5 or 6 Nobel Prizes from the past hiding in the development of those different techniques. So this is a schematic starting from the oven with hot atoms to the trapping region with very cold atoms of a fairly typical quantum gas experiment. And then this is what that same experiment actually looks like in real life. Not anymore, it looks much messier now. The picture was taken many years ago when it was still tidy. So what you're looking at here, just to orient you, is an oven on the left where we heat up lithium to about 1,000 degrees Kelvin. It propagates in an atomic beam down this long pipe and is trapped in a region over at the right. So here's the oven under the tinfoil. Here's the region of the atomic beam, and over here is the trapping region where we trap and cool the atoms. And you can see in this picture that there's a good bit of complexity in just making these experiments work in terms of electronics, quite a lot of optics, designing magnetic subsystems, mechanical and thermal subsystems, and so on. So these experiments are tabletop, but only if you have a decent sized table. A typical experimental sequence for a degenerate quantum gas experiments looks something like this. You start at 1,000 degrees in the oven. These are pictures of atomic beams of lithium and strontium in our lab. And then you do various stages of laser cooling, which could involve, almost always involves magneto-optical trapping, sometimes involves sub-Doppler cooling, sometimes magnetic trapping. And then the atoms basically get colder and colder. Typically, there's an evaporative step, although not absolutely always, which is a very powerful cooling technique, which is the same way that my cup of tea has cooled down to become undrinkably cold at this point. And at the end, you have Bose condensation, and that gives rise to some gas once you've gotten it to high enough phase space density, low enough temperature and high enough density that it Bose condenses. And these are momentum space pictures of a lithium-7 and strontium-84 BEC in my group. And we're starting to cool potassium now, and those are our 3 atoms. So I know we're getting towards the end of the hour, so maybe I'll actually the talk will divide pretty neatly between these 2 halves, between today and tomorrow. And I'll just say 2 types of things that people do with these neutral atom experiments before pausing to see if there's questions at the end. So the first kind of thing that people do is quantum simulation of solid state physics. And this kind of quantum simulation, which has now, actually, it's a relatively mature field, it's been going on for about 20 years, is based on an analogy. And this is the analogy between condensed matter, which is atoms packed into a lattice in a crystal, and the type of artificial matter that you can make in a neutral atom experiment. So that's made of atoms trapped in an optical lattice instead of atoms bound by Coulombic forces. And there are many, many differences between these 2 kinds of lattices. The most important is the density. An optical lattice, like the one pictured at the right here, is 100 million times less dense than the lattice in a crystal of silicon, which is what's pictured at the left. But the hope and the promise of quantum simulation is that there are enough similarities between these 2 types of systems that you can apply the precision and control of cold neutral atom physics to study problems that are relevant and interesting because they also occur in real materials. You can realize Hubbard models, you can study localization, which is a lot of what I'll be talking about tomorrow. You can study fun things like quasicrystals and quantum phase transitions, which I'll also be talking about tomorrow, and many other things that I won't be talking about. So this is, one way to look at this field of quantum simulation, is that it's really based on this analogy between lattice trapped atoms and actual electrons in crystalline lattices. The second topic, which is overlapping, but I think a really important one for cold neutral atoms, is quantum dynamics. And I think if you're at this, attending this talk at this ICTS program, you're probably already convinced that dynamics is an interesting thing. It's in any case true that following the dynamics of a many-body quantum system is quite challenging. It's pretty easy to move beyond what's possible to follow with a computer, and it's also very interesting. So there's things like how quantum thermalization proceeds, the physics of localization and many-body localization, how entanglement evolves in a many-body system, the emergence of quantum chaos, and the effects of measurement and feedback on a dynamically evolving system. Some of these questions are really at the forefront of modern physics, and it's neutral atoms make a really good tool for investigating them because we can control them so well, and we can drive them out of equilibrium so well, and the timescales are extremely tractable. Usually, if you're messing with a quantum gas in a way that's relevant to this kind of experiment, its response is going to be at millisecond scales, and that's super easy to see and measure. So a lot of experiments of this dynamical type that would be possible to imagine in a solid, but never possible to perform in a solid because we can't move stuff around fast enough, is sort of trivial to perform in a trapped neutral atom system. Okay, so I think maybe I'll wrap it up there since I'm almost an hour in. I got through the introduction to cold atom quantum simulation, and then tomorrow I'll plan to pick it up again with the more of a traditional research talk, talking about some recent results from my group on localization and driven quasicrystals. But for now, let me pause and see if there's questions or discussion of any of the stuff I said in this first hour.
There's some questions, yeah.
Hi, David. I didn't want to sidetrack you during your talk, but I got really interested in how do you actually cool down nuclei? Right? You mentioned you have a backup slide. Maybe you can explain it?
Oh, no, that was actually a joke. When I said that, I was talking about nuclear energy levels, which are like not useful bits of human technology, except for, rather nasty technologies. But I just, all I wanted to say about that is, bound assemblies of protons and neutrons have excitations, just the same way that, electrons around a nucleus have excitations. They're just much higher energy. So if we had the right kinds of lasers and so on, there's no reason that we couldn't play with those in the same way that we play with the internal structure of atoms to cool them down and control them and interface
so the
with them.
physics is literally the same, like mathematically it wouldn't be that much different, or?
In the sense that any finite volume quantum system is going to have, discrete energy levels. It's the same to that extent. It's, it's different forces. Nuclei are very complicated and interesting, but yeah, it's a little bit of a slightly jokey point relevant to like very far future technologies. But I do think like, there's nothing physically impossible about using nuclear energy levels to store quantum information and do tricks in the same way that we use electronic energy levels. It's just beyond our current technology.
Thanks.
So, the closest to realization is this thorium-229 business, where people are thinking of making a nuclear clock using this transition that happens to be very, very low energy, probably, I think it's sort of tens of eV in this one particular nucleus. But this is a hot topic of current searching for people who do this kind of thing.
Hey, I wanted to ask you a question about the quantum simulation part. So are there any examples of current quantum simulations in any platform that have outperformed the best available theories or computational capabilities? And do you think that there is a possibility that that may never happen? Like,
I think it's certainly, well, my answer to the second part would be no, because I would say that it already has happened. If I interpret the question right, what you're asking about is something that one might call quantum supremacy of a quantum simulation experiment, where you answer a question that you couldn't answer in another way. Is that the kind of thing you're asking?
Yeah, maybe say for the sake of argument, yeah.
So in this area, dynamics is a good place to look. And Emanuel Bloch's group in Munich has done some beautiful work on dynamics, which they sort of coupled with some quantum, some theory work following the dynamics of their interacting many-body quantum system. And they showed in those works, which are already now several years old, that they could move pretty straightforwardly beyond what was theoretically tractable just by waiting longer. Let things build up, let the system evolve further. You can still measure what it's doing, but you can no longer really follow it with realistic supercomputers. So one can do this kind of thing. It's a little tricky to, have observables that are well-defined enough that you can really say you're making predictions that the computers can't follow, but that's a feasible thing. The other thing I'll say is maybe the most famous example here of quantum simulation is the study of the superfluid to Mott insulator quantum phase transition. So in one sense, that phase transition was already known about before people did this. Marcus Greiner and Emanuel Bloch and others did this with cold atoms. So, Matthew Fisher and other people had figured that out earlier, that there was going to be this kind of phase transition. But in another sense, and to me, this is more relevant to the way science really proceeds, we understand way more about quantum phase transitions and about the superfluid Mott insulator phase transition than we ever would have if we hadn't had this productive arms race between quantum Monte Carlo and cold atoms that sort of got better and better throughout the 2010s, and resulted in a really good quantitative understanding of what happens at that quantum phase transition. So that's maybe not such a direct answer to your question, but that's an area where I think it was often the case that the experiments would be followed by theories that would then go a little further. Then the experiments would go further and the theories would go further. But actually, that was a really productive way to learn about the science. So for me, that's often how quantum simulation operates, is not by saying like, what's the answer to what's this spin going to be after waiting for 20 seconds in this complex interacting system. It's more working hand in hand with theory and complementary techniques in a way that kind of where the different techniques challenge each other and you end up understanding things better. I'm sorry if that answer is a little bit Pollyannish, but that is actually what I believe is more the real world utility of quantum simulation experiments often.
Hi, yeah, so my name is Archuk. So I have a question, like, so in these things, like what kind of things can you measure and how do you measure? So is measurement like always destructive, or can you do some continuous measurement or something like that?
Yeah, okay, great question. I didn't say anything about that. So in a neutral atom experiment, the measurements are commonly optical. So the pictures at the lower right here, which are from Marcus Greiner's quantum gas experiment at Harvard, were taken by scattering light off the atoms trapped in the lattice and then collecting that light onto a camera, just very similar to the cameras we have in our phones. That kind of measurement can be destructive or non-destructive depending on how destructive it is to scatter photons off your atoms. So it destroys certain delicate features of quantum phases for sure, but it doesn't have to make the atom go away. Actually, each of the little green dots in this image is a rather large number of photons, between dozens and thousands, all of which scattered off this one single atom without like kicking it out of the trap. So in that way, things can be done sort of non-destructively. It's also possible to do gentler optical imaging techniques, which are dispersive and which cause the atoms to give rise to an effective index of refraction rather than actually scattering off them. And then that kind of thing, you can actually preserve a Bose condensate and preserve quantum coherence while still getting some information out. So I think it's a fascinating question, in particular for the field that I myself am very interested in right now, which is interactive dynamics. What happens if you measure a system like this while it's evolving, but not totally projectively, and then feedback the results of those measurements to the future system parameters? To do that kind of thing, you need exactly the sort of gentle measurement that you're suggesting, and that is possible. And then let me just add that not every measurement technique is optical. There's beautiful experiments, for example, in France, using metastable helium condensates, where in order to image with extreme precision and beauty the arrangement of their atoms, they actually drop them onto a microchannel plate, because a metastable helium atom has a gigantic amount of energy stored in its electronic structure. It's Hal Metcalf calls it the only true atomic bomb. And so you can actually image those atoms one by one, falling onto something that looks like a particle detector. That's a very unusual experiment, but people do that, and people do electron beam imaging and microscopy of quantum gases in Kaiserslautern. There's a few other fascinating possibilities, but dominantly it's done by scattering visible light off of the atoms, and that can be destructive or not destructive depending on how you set it up.
Thank you, very interesting.
I see no more questions. Are there more questions? Oh, there is one.
Thank you. So you were just mentioning about this, how we want to use cold atoms for quantum simulation. And I guess the question is that one of the ideas was that you want to actually simulate the Hubbard model, right? And we could not really get down in temperatures. So I was just wondering, what's the current status? What are the sort of, because we've moved on to quantum dynamics a lot, but are there efforts underway to actually get the temperatures of these fermions down to really get the Hubbard model phase diagram?
Yeah, great question. So let's see, I often have this slide, but I don't think I have it in this deck. So for those of you who aren't familiar, the doped antiferromagnetic Hubbard model is predicted to potentially exhibit D-wave superfluidity, which could help explain the physics of cuprate high temperature superconductors. And it was very hard even though our atoms are sort of at the nanokelvin range, they're actually quite hot compared to a typical cuprate superconductor. And it was very hard to get down to the necessary temperature range, which was on the order of tens of picokelvin. for the typical densities in a rubidium-based optical lattice experiment. And the state of the art is people like Randy Hewlett and Marcus Greiner have done really nice work continuing to pursue this, and started to see antiferromagnetic correlations persuasively emerging. So then you're getting below the Néel temperature, or around the Néel temperature in the relevant Hubbard model. Of course, the temperature of D-wave pairing is some relatively significant factor smaller than the Néel temperature, and that's not something that has been achieved yet. I would say work is ongoing. It's a major technical challenge. I think at some point, if you're talking about hundreds or tens of picokelvin, your experiment is just going to take a long time, because the time scale that is associated with that low an energy scale, it actually gets to be like kind of long. So at some point, progress in that area is going to have to come by packing the atoms closer together using maybe plasmonic structures or something like this, and boosting the energy scales up again. Because of course, the only reason the energy scales are so low is the low density of the trapped atoms. So if you can get them closer together, use lighter species, this kind of thing, then you can get those temperatures up and hope to reach the relevant regimes. Or maybe the new Rydberg interaction platforms give you much higher energy interaction knobs, and potentially one could realize something that's relevant to that same Hubbard model using a new tool of interactions.
Thank you, David. I see no more hands. Are there more questions? If not, let's thank David. And well, thanks. It was very entertaining, and let's see you tomorrow.
Yeah, thank you guys. Thanks for a lot of really great questions. And again, apologies for missing the talk in person, but I'm glad it worked out to have such a good discussion virtually.
See you tomorrow, David.
See you guys tomorrow. Thanks.